Welcome to Unit 2, and in this unit we're going to be learning everything about Unit 2 for AP Biology. So yeah, please feel free to join, and I'll see you on the other side. Now, for tonicity review, and remember tonicity is relative, so we need to be able to compare it between two solutions, okay? And this is on the outside of the cell, and this is on the inside of the cell. So the first one, a hypertonic solution on the outside, where would the water move? Okay, here I can see this is a hypotonic solution because it has less dissolved solutes. And here I have a hypertonic solution because it has more dissolved solutes. And water always wants to move, okay, from a hypotonic environment to a hypertonic environment. So if it's hypertonic outside, water would move into the cell. Next, a hypertonic outside. So here we can see there are more solutes dissolved. So this is hypertonic. That means the inside of the cell is now hypotonic. And water always wants to move from hypotonic to hypertonic. So it's going to move out of the cell. Okay. And remember, it's the water that moves. It's not the solute. And then finally, the isotonic outside will have a net water movement into and out of the cell. So the cell would stay the same size. It's not going to grow. It's not going to swell. Okay. It's not going to shrink. It's going to stay the same size. Okay. And this is my isotonic solution because the amount of solutes outside is equal to the amount of solutes inside, which means that if a water molecule moves in, a water molecule will move out. Okay, it's going to have no net water movement. It's going to stay the same size. Now, we linked in tonicity with the water potential. Okay, now water potential tells us about the tendency of water to move. And water that moves, we call osmosis. Okay, very important. Now, to calculate the water potential, we use the pressure potential. Okay, and the pressure potential will be applicable to organisms that have cell walls. Okay, because remember, if water moves into this cell, okay, it creates pressure on the inside, on the cell wall, because the cell kind of wants to expand. It wants to get bigger, but this cell wall is a support structure, okay? And so because the cell inside is getting bigger, but the cell wall is a rigid structure, pressure inside builds up, and we call that turgor pressure. Okay. And then finally, we also calculate the water potential by adding the solute potential. Now, this is the effect of dissolved solutes. So if I have more solutes, it would lower the water potential. Okay, and water would always move from a high water potential to a low water potential. The highest water potential can get is 0. And it will always move to a number that is negative. Okay. Why I say the highest water potential is 0, I'll show you when we do the formula. Or I can just explain it here. So to calculate the water potential, if it is in an open container, then the pressure potential is 0. Okay. But the solute potential depends on the amount of solutes that are dissolved. And in a solution that's pure water, meaning there is no solutes dissolved in it, okay, the solute potential would be 0. So the highest the water potential can get is 0, and it will always move to a lower water potential. Let's do this example. So here is solution A, okay, and solution B. This solution has a water potential of minus 0.3 megapascal, and this one has a water potential of minus 0.9. Now, we know that water would always move from a higher water potential to a lower water potential, and 0.3 is higher, okay, than minus 0.9. So these water molecules are going to move across this selectively permeable membrane into the other solution. Now, what is important to remember, it is not these solutes that move. Okay, these solutes are not moving across the membrane because they can't move across the membrane. And because they can't move across the membrane, because over here I have a high solute concentration, and over here I have a low solute concentration. So just by diffusion, the solutes would want to move that way, but they can't. The water is the only thing that can move. So because water is moving, we call that osmosis. And then here, the water would move from solution A to solution B because water always moves from a higher water potential to a lower water potential. Now, let's calculate the solute potential. So remember, we have the water potential equals the pressure potential plus the solute potential. We are going to assume this is 0 because in an open container, the pressure would be 0. But if I have a cell wall, okay, and I have a vacuole that's filled with water, it creates this pressure on the cell wall, and then I can't ignore that the pressure potential. Okay, I would have to add that in. But otherwise, we can just assume that it is 0. But we do need to be able to calculate the solute potential. And it starts with a negative number, which means already if I increase one of these, it will become more negative. And if I decrease it, it will become less negative. The I is the ionization constant. Okay, and just how many ions does this molecule create? So for example, if it's just 1, it means that if I put this in water, it would just make 1 ion. Okay, and if it has a ionization constant of 2, that's like sodium chloride, that means if I put sodium chloride into water and it dissolves, it will create 2 ions, sodium and chloride. There's more particles for the water to interact with. Next is the molar concentration. So this is the number of moles of solute per liter of solution, and they will always give you this concentration. The pressure constant is always the same, and the last one is temperature. Now, what is important to remember is that the temperature is in Kelvin. So you need to take the degrees Celsius plus 273 because you need to work it in kelvins. Okay, so for example, if my molar concentration was 0, because this is pure water, it means that my solute potential is 0. If I increase the concentration, let's make it 0.2, okay, then the solute potential would be a negative number, okay, but it would be a small negative number. If I increase, so if I make it small, like 0.2, it will be a small negative number. If I increase this value, it will make it more negative. Okay, so that is why we calculate the solute potential, because as soon as there is a substance dissolved in it, it will have a negative value. Let's do this worked example together. So I have 0.3 molar of sucrose solution at 25 degrees. And then they will give you the ionization constant, which is 1. So the ionization constant is 1. It's 0.3 molar. And then this constant is always the same because it is a constant. So 0.831. And the temperature should be in Kelvin. So that's 25 plus 273, that's 298. So I just rewrite this in 831 and 298. And if I calculate this, I'll see that it is minus 7.43 bars. Okay, so the solute potential is minus 7.43 bars. This means that the solution has a negative water potential because it contains dissolved solutes. And if I add more solutes, okay, it will become an even greater negative number, okay? And if I take solutes away, this negative number would become smaller. If you enjoyed today's lesson, please don't forget to like and subscribe, and come join us on the Skool.com community page where you'll find AP Bio blueprints. And if you take a look inside, you will find that Unit 1 is completely free. See you there.